In this video, I'm going to be going over linear speed and angular speed. And we want to talk about how something that is in motion, how we can measure their speed in each of these ways. So before we get into calculating these, we just need to remember what each of these types of speeds represent. So if we're talking about linear speed, what that means is the change in distance divided by the change in time, right? So some common units for linear speed are miles per hour, or maybe kilometers per hour, right? It's these are both measuring a distance divided by a unit of time. Maybe meters per second, that's another common one. If we're talking about angular speed, what we're saying is, well, how is the angle changing as time changes? And so this really only is relevant when the motion is taking place along a curve or along a circular path. And the two units that we'll see for angular speed are, let's see, the change in, or we'd say radians per unit time, so maybe radians per minute or radians per second. I guess it could also be degrees per minute or degrees per second. Okay, so how is the angle changing per unit time? So we'll go through a few examples of these types of questions. So the first example says, suppose a runner runs in a circle that is 100 feet over 5 seconds. What is the linear speed of the runner in feet per second? So this first one says, what's the linear speed? And then the second question is the same situation, but what's the angular speed or angular velocity? Now, these types of questions, we really need to pay close attention to what the units are that we're dealing with. So this is feet per second. So remember, linear speed is the change in distance. In this case, it's the change in the number of feet divided by the change in time. Okay, so we have 100 feet divided by 5 seconds. If I reduce the 100 over 5, I get 20, so 20 feet per second. That is probably not anything very surprising. You've been doing these types of speed calculations in many previous classes. What is new, though, is what happens when we want to know what the angular speed is. Now, what this is asking us to do is we have a circle. Imagine that that's a circle. Actually, let me see if I can do a better job. There we go. So we have a circle, and the runner runs 100 feet. So let's say they start here, and maybe they end up over here. So that is 100 feet. And then it says the radius is 40 feet. And this is over 5 seconds. So what's happening is, for angular speed, we want to know what is the angle that this runner passed through as they run along this path. Okay, so what is the angle change that has happened over 5 seconds? Okay, so what we can do is we can recall our arc length formula. The arc length is equal to the radius times that central angle theta. We're going to do this so that we can find out what that angle is. So the arc length here is 100 feet. The radius is 40 times theta. So I get 100 over 40 is equal to theta. I can reduce that to 5 halves. So 5 halves radians is the angle that this runner has passed through. So 2.5 radians. So 2.5 radians divided by the change in time. And let me just remind us. Let's see here. What am I doing? I want to, there we go. I want to grab this, move it over. Okay, so remember, if we're talking about angular velocity, that's the change in angle divided by the change in time. Okay, so the angle that this runner has passed through is 2.5 radians over 5 seconds. So the angular velocity here is 0.5 radians per second. Okay, so again, the key thing to remember is that when we're talking about angular velocity, it's always the change in angle divided by our unit time. Okay, and then we'll go through a couple more examples of this. This first one says find the angular velocity in radians per second. So radians per second is what we want for the tip of a 22-inch lawnmower blade that is rotating at a rate of 2,500 revolutions per minute. Okay, so what's happening here is, let's say, here's the path of the lawnmower blade. Whoa, I don't want that shape. Let me just do my best here. So we have a circle. So our lawnmower blade is here, and it's rotating. Let's say it's rotating that direction. And the length of the lawnmower blade is 22 inches. So that means the radius here is 11 inches. Okay. And the other piece of information we have is this 2,500 revolutions per minute. So I'm going to write that 2,500 revolutions per minute. And what we want to do is, so what that means is this lawnmower blade is, in every minute, it's turning 2,500 times. And so what we want to do is we want to end up converting that 2,500 revolutions per minute into radians per second, because that's the unit we're looking for. Okay, so what I need to do is I need to change that minutes into seconds, and then somehow convert the revolution unit into a radian unit. So the first thing, and probably the easiest thing, is to change that minutes into seconds. So I can use a conversion factor, minutes over seconds, and 1 minute is equal to 60 seconds, and that will cancel out the minutes. So if I just multiplied these two fractions together, I would end up with a unit of revolutions per second, which is not quite what I want. But I want to somehow change this into radians from revolution. So if I multiply this way, the revolution will cancel here. And now multiplying just these units, I'm going to end up with radians per second. Now I need to figure out how many radians equal 1 revolution. Well, in other words, what is the angle that this blade passes through when it makes 1 revolution around the circle? Well, 1 revolution around the circle is 2 pi radians. So I multiply by 2 pi over 1 here, and that is going to give me radians per second. So multiplying 2,500 times 1 times 2 pi and then dividing by 60, I end up with 261.8 radians per second. Okay, so to convert between angular velocity and linear velocity, we have a simple formula. So the velocity is equal to RW, where V is the linear velocity, R is the angular, that's the radius. R is the radius, and it looks like a W. I think it's a Greek letter, but we'll just say it's W, and that's the angular velocity. Now, if I wanted to convert this 261.8 radians per second, if I want to convert that into a linear velocity, I can just use this formula here. So I'm looking for a linear velocity, so V. The radius here was 11, and the angular velocity was 261.8 radians per second. So our velocity here, I don't know if I have a calculator that works. 261.8 times 11, 8162, 89782. So we end up with 2,879.8. And then the key here is to realize what the units are. So this is inches. The radius was inches. And so this is inches per second. Okay, so that's how we can go between linear velocity and angular velocity. All right, and then we have one more example here in this video. It says a model plane is attached to a swivel so that it flies in a circular path at the end of a 12-foot wire at the rate of 15 revolutions per minute. Find the angular speed and the linear speed. Okay, so we have this. So we have an airplane here. I'm not a great artist, but imagine this is our airplane. Okay, and it's flying around in this circular path like this. And it says the wire here is 12 feet, and 15 revolutions per minute is our current velocity. Find the angular speed and the linear speed. So for the angular speed, remember angular speed is change in the angle divided by the change in time. Okay, so I have 15 revolutions per minute. This doesn't say what unit to find the angular speed in, so I'm just going to have it be, our unit of time be minutes. Okay, so that I don't have to change that. And then 1 revolution of that airplane is equal to 2 pi radians. Okay, so revolution cancels here. I get 15 times 2 pi. So 15 times 2 times pi. We end up with roughly 94. So 94.25 radians per minute. Okay, so that's our angular speed. For the linear speed, remember that's the change in distance divided by the change in time. So I'm still going to start with 15 revolutions per minute. And I want to end up with some distance. I'll use feet because that's what our unit is for the radius. So feet over minutes is what we'll end up with. So I don't have to convert the minutes into a different unit of time, but I do need to convert that revolution into a distance in feet. Now this is where things get a little bit tricky. Nope, I don't want feet down there. I want revolution down there. So 1 revolution. Now the question is, what is the distance that this airplane has traveled after it's made 1 revolution? Well, that distance in a circular path or in a circle is the circumference. So the circumference is equal to 2 times pi times r. And the radius is 12, so this is 24 pi is what our distance is that this airplane has traveled. So 24 pi feet is what we have here. So the revolution can be eliminated here. So then I just have 24 pi times 15, and we end up with 1,130.97 feet per minute. Okay, and the last thing to mention here is that, remember, we can convert, or we have an equation, this equation up here, linear velocity equals radius times angular velocity. And so this is a way that we can check that our answers are correct. So the linear velocity is 1,130.97 is equal to the radius, which was 12 times the angular velocity we found, 94.25. And if you multiply those out, the left side is equal to the right side. So that checks out. Our angular and our linear velocities seem to be correct.